In this lecture, we will derive the boundary conditions for electrostatics. As I've already told that the Maxwell equation in differential form are point equations, that is they are valid at every point, but they do not contain the information of discontinuities. So to find this boundary conditions, we have to use the integral form of those equations so that we can find the discontinuities in them. So let us take an interface of two media. Let us say this is medium 2, this is medium 1. So the outward normal for medium 1 will be in this direction. So this is AN1, and outward normal for the medium 2 will be in this direction. This will be AN2. Now let us try to find the boundary condition for the tangential component. For that we will use the conservative property of the electric field intensity. So we will make a loop A, B, C, D, A. Let us say this loop has a width delta W and has a height delta H. So let us say this is E1 and this is E2. So using the definition or integral form of Maxwell equation for this loop A, B, C, D, A, B, C, D, A is equal to 0, what I will have E1 dot delta W. Now delta W in this vector is equal to minus of delta W in this vector. So these two vectors are equal but opposite in direction. So what I will have for this part, let us say if it is E1 dot delta W, so for this part it will be E2 dot minus delta W plus E field dot delta H plus E field dot delta H. Minus sign will be there. If this is plus delta H, this will be minus delta H, and it should be equal to 0. Now for the limiting case, when delta H tends to 0, that is this loop has a height very small, so this delta H will go to 0. So this term is 0 and this term is 0. So the remaining terms is E1 minus E2 dot delta W is equal to 0. Now you see that this dot product is going to give us the component of this E1 and E2 which are along this delta W, that is the tangential component, the component in this direction. So this is going to give us E1 tangential minus E2 tangential delta W is equal to 0 by removing the dot product. Now this delta W is not 0, it implies this is equal to 0. E1t minus E2t is equal to 0. So this implies that E1t is equal to E2t. So you see that the tangential component of electric field intensity is continuous along the interface in electrostatics. So now we know that D is equal to epsilon E. So I can write it as D1t by epsilon 1 is equal to D2t by epsilon 2. So this is the first condition for the boundary for the tangential component. Now let us try to derive the boundary condition for the normal component. So for that, what we will do, we will make a pillbox, very small pillbox. Again, this is medium 2, this is medium 1, this direction is A and 1, this direction is A and 2, and this is pillbox. This is delta S A and 1, this is delta S A and 2 in vector form, because A and 2 is in this direction and it's this area is taken in this direction. and this height is, let us say, delta h. I am assuming that this surface is having a surface charge density sigma s. So this surface is going to have a charge equal to delta q is equal to sigma s delta s. So using the Gauss law in integral form, d dot ds along this surface s is going to give the total charge enclosed, or equal to sigma s delta s. So I will have d1 dot delta, let us say this is d1 and this is d2. So d1 dot along this surface delta s an2 plus d2 dot delta s an1 plus d dot curved surface area should give me sigma s delta s. Now for the limiting case, when this delta h tends to 0, this curved surface area will be going to 0. So this is going to 0. So I will have d1 delta s an2 plus d2 dot delta s an2 is equal to sigma s delta s. Delta s is cancelled out. Now I will use a an2 is equal to minus of an1. So d1, now this dot product d1, the dot product d1 dot an2 is going to give us the normal component of d1. Similarly, d2 dot an2 is going to give us normal component of d2. Now using this an2 is equal to minus an1 or an1 is equal to minus an2, so I will have an2, I will take common, and I will have d1 minus d2 is equal to sigma s. I have taken an2 common and I have replaced this with, this was an1, sorry, so I have replaced it with a minus of an2. So this is d1 minus d2 dot. So changing this dot to the normal component, I will have d1n minus d2n is equal to sigma s. So you see that the normal component of the electric flux density is discontinuous along the interface, and this discontinuity is equal to the surface charge density on the interface. If there is no surface charge density, then these two are equal and these are continuous. So in this way we have found two boundary conditions. What are those? That the tangential component in electrostatics for the electric field intensity is continuous, and the normal component are discontinuous with discontinuity equal to the surface charge density. Or in vector form, what I have, an2 dot d1 minus d2 is equal to sigma s, and it is simply e1 minus e2 delta w is equal to 0. So this is the boundary condition. Now in next slide we will solve a numerical example. Now let us see this numerical example. What we are given? We are given an interface with the media epsilon1 permittivity and with another media having permittivity epsilon2, and we are given that there is no surface charge density on the interface. What we are asked to find? We are asked to find the magnitude as well as direction of the electric field intensity at point 2 in medium 2. So at this point P2, we have to find electric field intensity and its direction. And we are given this is angle alpha 1 and this is angle alpha 2. So from the boundary condition that E1t is equal to E2t, we can write now E1t is this value and E2t is this value. Now we have to put both of them equal. So E2 sine alpha 2 should be equal to E1 sine alpha 1. If it is an angle alpha 1, this angle will be 90 minus alpha 1. Similarly, if this is angle alpha 2, this will be 90 minus alpha 2. So this thing, if this is E2, this will be E2 sine alpha 2, and if this is E1, so this will be E1 cos 90 minus alpha 1 or E1 sine alpha 1. So E2t is equal to E1t should give this value. Further, we are given that sigma s is equal to 0, that is there is no surface charge density on the interface. So it implies d1n is equal to d2n. Now this is E1n, this is E2n. Now it implies epsilon 1 E1n should be equal to epsilon 2 E2n. Now putting the values of E1n is this. E1 sine 90 minus alpha 1 should give you cos alpha 1, epsilon 2 E2 cos of alpha 2. So this is equation 1 and this is equation 2. So dividing 1 and 2, what I will have, tangent alpha 2 over tangent alpha 1, it should be equal to epsilon 2 over epsilon 1. And E2 should be equal to E2 t squared plus E1 t squared, or it will be E2 sine alpha 2 squared plus E2 cos alpha 2 squared, or it should give me E1 sine alpha 1 squared plus epsilon 2 1 by epsilon 2 cos alpha 1 E1 squared and whole to the power 1 by 2. Or I'm just putting the values, I'm doing nothing. I am putting this epsilon 2 alpha 2 in terms of epsilon 1 E1 using this equation here. So in this way, E2 is found out to be E2 is equal to in terms of E1 sine square alpha 1 plus epsilon 1 by epsilon 2 cos alpha 1 squared 1 by 2, and the angle is alpha 2 is equal to epsilon 2 by epsilon 1 tangent alpha 1 and tangent inverse. So in this way we have found E2 and its direction in terms of epsilon 2, epsilon 1 and E1. So you see, this is some kind of Snell's law which is being followed here, and by examining the figure also or the various angles, we can find which one is greater, whether epsilon 2 is greater or epsilon 1 is greater, just by looking the relation tangent alpha 2 by tangent alpha 1 should be equal to epsilon 1 by epsilon 2. We can find which one is greater. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join us on our Telegram group, whose link is given in the description of this video. Thank you.